next contribution comes from Millennium Petrochemical by Steve, the author is Steve Augustine. And the topic is a scale-up of an improved vinyl acetate catalyst.
Well, this talk is in many ways maybe a little bit more pedestrian than what we've heard, but what I want to talk to you about, I want to preface by the fact that for me, and this is a surprise to me, is that this is somewhat of a bittersweet opportunity, and I've had an opportunity to talk to some folks this morning, but as Raul said, the sweet part is that it's very enjoyable to be a part of this Catalysis Club, Catalysis Society, and I guess I've become one of the old-timers here because I can look back now on 13 years of coming to the spring symposium. The better part is that a couple things. One is that Millennium Petrochemicals, as Raul introduced me, no longer exists. We've kind of been absorbed into Millennium Chemicals, and as a part of that, we're also going to be absorbed into a laboratory in Baltimore, so this will be my last opportunity to be with you all as a member of the society. Hopefully I can come back and visit sometime. But kind of appropriate to that is that what I'm going to do is kind of fill you in on a project that we have finished off. And the project has to do with vinyl acetate production, synthesis, and the culmination of what we would call a third generation catalyst. In fact, in the next couple of weeks, we'll be replacing our second generation catalyst in the reactor with this third generation catalyst. So I expect to be either very excited or very sleepless this next month as we see how this really works out. To give you a feel for what vinyl acetate is, I'll begin just with this simple reaction chemistry. It is a unsaturated molecule made by the combination of ethylene and acetic acid in the presence of oxygen. We use a palladium gold, supportive palladium gold catalyst in which we promote with potassium. And it makes vinyl acetate, and the driving force there is the production of water. The competing reactions which we want to avoid is combustion of the ethylene to make CO2 and water. Can you see okay with you? Am I flat? Gary? Okay. All right. Again, just to give you a feel for why we make this material. Primarily, vinyl acetate goes into the formation of polyvinyl acetate, emulsions, lattices, things that go into water-based paints, water-based adhesives, and in fact the growth in the vinyl acetate market has come with these new environmentally friendly methods to paint your house and seal your windows. We also is used to make polyvinyl alcohol. You do the polymerization, then you hydrolyze the acetate group, and again, things that are very important like architectural glasses, automobile windshield protection, polyvinyl made by DuPont. Also some sizing, adhesives, and those types of things. Also, it's made in the combination of ethylene to make copolymers. The way we began this work is actually by looking at the patent literature. And we saw some patents here, I just used the numbers, of a competitor of ours, and it kind of sparked some curiosities. If you're familiar with patenting, as probably most of you are, a lot of times you find an interesting application, and then you try to cover as broad an area as possible by postulating that that type of reaction can go on in different areas. The one thing that these folks said is that if you combine palladium chloride, and what they wanted to do is precipitate palladium onto a support with sodium hydroxide, making that palladium insoluble. But they said also if you use sodium carbonate, you can imagine that you get disproportionation of water, make the palladium hydroxide, and salt and CO2. Whereas we thought, it'd be kind of interesting if that didn't happen. And what would happen as opposed to that would make if you just make the carbonate. And the reason that would be interesting is if you can imagine some type of palladium carbonate, as I kind of sketched out here, and this is completely imaginative at this point, that once you reduce this to get the palladium metal, and that's in fact what we do want for the catalysis, that you would get all sorts of defect sites and problems as this carbonate collapsed into the zero valent metal. And so if we could then make this material, reduce it in the right way, prepare it in the right way, maybe we'll get a lot of those defect sites, corners, steps, those types of things that are very interesting for catalysis. And so we started, and the first thing we started with was something very simple. Is a simple titration. Aqueous phase titration using the metals as the acids in this case, and titrating with sodium carbonate. What you would expect, again, if you would precipitate the hydroxide, you would expect that you would make some CO2, and you would see some effervescence. It would bubble. But on the other hand, if you would make the carbonate, and I hope you all can see that, you wouldn't see the effervescence. Essentially, you would deposit the carbonate, and the CO2, instead of bubbling, would be in the solid. Well, what we saw is as we titrated it, when we were in the very acidic point, we did indeed see effervescence. The acid strength of these two metals was so great that the carbonate did break down. But the point where we saw precipitation of the metal salts, there was no effervescence at all. So we thought, well, that's a preliminary result, and it's kind of encouraging. It looks like we're making the carbonate. Another way to look at it is take it and look at it with diffuse reflectance infrared. And you can expect that if you're making some type of metal carbonate, it would have an interesting absorption. And what we see here is this 1450 wave number is the sodium carbonate absorption. If we titrate that with gold chloride, we see a band or shoulder form here at 1570, and then we have an excess of carbonate here that's still apparent at 1450. Do the same thing with palladium. And again, as we titrate that carbonate, we see that we get a doublet, two bands of the palladium, what we think is some type of palladium carbonate type species. We don't know what the structure is at this point, but also the sodium carbonate. And then as we titrate the entire sodium carbonate presence, we see the bands here at 1615 and 1413 much more pronounced and apparent. So again, we see with just a simple titration that appears we make a carbonate, and then with infrared, we see something that looks like a carbonate. Now, the classic test for carbonate is a thermal decomposition. Again, very simple. So this is a temperature program reaction in nitrogen, and we monitor it with a mass spectrometer, and we just look for CO2 coming off. And essentially what we see is that when sodium carbonate is alone, we see a desorption here, which is due to the desorption of water and CO2 that is present in the water, but that the sodium carbonate itself is very stable and does not decompose, at least on aluminum, until about 650, 700 degrees C. When gold is present, we see a structure in here, a very broad diffuse decomposition of that gold carbonate. But we were very interested that when we looked at the palladium species, we saw a very sharp decomposition here at just about 200 degrees exactly, and then a more diffuse decomposition. And again, in all these you see that we have excess carbonate present. So it looks like, yes, we've seen with titrations, we've seen with infrared, and we've seen now with just simple decomposition that it sure looks like we're making some type of metal carbonate as a precursor to this catalyst. What we thought was interesting is that what would happen if we just focus on that decomposition, that sharp decomposition. That was an interesting species for us. And so what we did is we thought, well, simple-mindedly, what happens if we first decompose an oxygen, as is the common practice, and then as we sweep the reactor with helium in order to not get an explosion, we can do that in two different ways. One is that we can sweep the reaction and then ramp the temperature in that inert, and therefore we are effectively ramping that catalyst as in its oxidized form. Or we could sweep at the temperature where we oxidize and then ramp as we are reducing. So again, very simple. Either we ramp the temperature in an inert or we ramp it in a reducing atmosphere. And what we found was very interesting. First of all, it might take some time to get used to these structures, but essentially it's just a three-dimensional plot where we plotted the reduction temperature here on the x-axis, oxidation on y, and then z gives you a feel for the activity. Okay. If you look at these, and somewhat cross-eyed, but for a little bit, you get a feel for the fact that if you have a reducing temperature that is at or below your oxidation temperature, there's no difference in whether you change that temperature as you ramp an inert or you ramp in hydrogen. And you see that this side as well is fairly similar. The interesting thing happens is when you reduce at a temperature higher than your oxidation. So here we have a 200-degree oxidation, 500-degree reduction. We get a very active catalyst if we ramp that temperature in hydrogen. On the other hand, here, when we reduce at 500 after we've oxidized at 200, ramping that temperature in inert, the activity is much lower. And so what we thought is, that's kind of interesting. Can we develop that further? How does that compare to our current catalyst? How does that compare to other folks' catalysts? So we scaled that up, at least to the big 100-gram size, and we see that, again, comparing our first generation, second generation, and now what we would call our third generation catalyst, that this catalyst does indeed, at these 100-gram levels, have a higher activity than do the prior two generations.
Steve, what's the length of the time that you ran these experiments? Is this a first GC shot, or is it 1 hour,
No,
2 hours online, and what?
These runs, the first ones I showed you were on the order of a few hours on time on stream. These are on the order of, this would be at least 2 days. So what we do is we try to hit a steady state. It takes us 2 days to hit that. And then they run for a period of about 500 hours. And indeed, conversion is not so important unless you can have the selectivity. And so we compared the selectivity of these catalysts. And again, this is a selectivity as a function of conversion profile. First generation catalyst, second would be the green, and then our third generation is at least as selective as a function of conversion as our second generation catalyst. So we were pretty pleased. Also, we wanted to see how we stacked up against other materials out there. And so we were interacting with the vendor at that point, and we said, give us your most active material and load it up with as much metal as you possibly can, because we want to see how the activity of your catalyst compares to ours. And so, again, this gives you a feel for time on stream. The top graph being a volumetric yield, space-time yield, grams produced per liter per hour. The bottom is normalized per gram of palladium. And what we learned is, even with our second generation catalyst, now in red, that the vendor's catalyst couldn't pack that much activity per volume of reactor. But our problem was right here, is that they were using palladium much more efficiently than we were. But then with this second, or this third generation, this improvement, we see that we do use that palladium much more efficiently. The problem comes in terms of how do you apply this. We have an existing process, and so you have a catalyst that's more selective. It's very easy to put into an existing process, but a catalyst that's more active can be very problematic in an existing process. The first problem, or the first thing to think about, is overconversion. And again, in an oxidation, the problem of overconversion is a loss of selectivity. You make a lot of CO2. But secondly, it's an exothermic reaction. And so when you're making all that CO2, how are you removing the heat? And there's a good potential for thermal runaway. So what we decided to do is to actually lower the activity of the catalyst by lowering our metal content. And in this case, with palladium and gold, it turns out to be very valuable to lower that precious metal content. We have another problem in that we're a very small research facility. We don't have a pilot plant. And so we didn't have the luxury of scaling up, as you go from a pound to 10 pounds to 100 pounds to 1,000 pounds, and on and on and on. We scale up generally from about 2 pounds, about 2 pounds to several hundreds of thousands of pounds. And so we needed to get a feel for the lifetime, the longevity of this catalyst under reactor conditions where we do mimic space-time and we do mimic linear velocity, which are both very important. So what we did is we kind of took the long way around and we used our existing reactor as our pilot facility. And so in November '99, we took 3 slightly different experimental catalysts and we put them in 6 tubes in a production reactor. One of the tubes contained a thermocouple, and that allowed us to monitor the temperature. The second tube was just a catalyst, and we removed that material after 2.5 months time on stream. Then the second sample was removed after about 7.5 months time on stream to get us a feel for how it was performing with time on stream. First of all, the temperature. What we're looking at here is the blue is the coolant temperature. The red line would be the temperature of the second generation catalyst. So you see the exotherm is a representation of how much reaction is going on there. And then the discrete points are the 3 different test catalysts that we put in. And so you can see a cycle here that's very typical from 3.5 to 7.5 months of reaction, regeneration, reaction, regeneration, reaction, regeneration. So as the catalyst deactivates with time on stream, we raise temperature, which is not too much unusual. But you can see that in comparison with the second generation catalyst, actually our third generation samples were performing better at the end of that regeneration cycle. In certain cases here, 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 here. So we had the impression that, again, we could mimic the performance of the catalyst, but there may be also a performance enhancement with this material. As I said, we removed samples from the reactor at 2.5 months and 7.5 months. And what we found is that as we tested those in the lab, that at 2.5 months, the performance, the productivity of our second generation catalyst, and in this case, what we're focusing on is our #1 test catalyst, were comparable. Maybe a little bit better activity out of the second generation catalyst. And then the selectivities are all comparable. But what we were starting to become pleased about is that when we took out that 7.5 month catalyst, the productivity of that test catalyst 1 was greater than our second generation catalyst, indicating that we did have a little bit longer lived catalyst at that point. And the selectivity is improved slightly.
What was the percent increase in productivity after 7 months?
We're talking on the less than 10%. So it's not a big change. And then we scaled it up. We thought at that point we had enough information. Can we then scale this up to understand or to make a production catalyst? And what I have here is the productivity of the catalyst under specific reactor conditions by our second generation catalyst, the third generation lab prep catalyst. You can't see those too well, can you? I was trying to find those, but yeah, those are the points you can't see at all. And then a scale-up version, and then the production batches. What you can see is that even with the metal load lowered by a factor of 25%, the productivities are just the same. And then as we have scaled it up, the company doing that has done a very good job, and actually it's gotten better and better with time. And the same thing, we've just seen the same thing with selectivity. And again, the lines here represent the means of those points. And so again, as we scaled it up, the selectivity appears to have improved from these batches. So again, I just wanted to give you a quick story of the finish of a lot of this work. And hopefully it will be finished, and we won't have to go back to the lab after we see how it works in the plant. But anyway, what we've learned is that you can precipitate with sodium carbonate, and it's probably not a surprise to you all, but we were quite pleased to know that you can make a palladium and gold carbonate, whatever that looks like, but it also offers a means to synthesize a highly active catalyst. as we've scaled that up and we've looked at the performance in our plant, the thermal performance of these experimental catalysts tracked and appeared to have exceeded that of our second generation catalyst. As we've scaled up, the reduced metal loading catalysts exhibit improved selectivity and productivity, and then the scale-up has been very, very successful. So with that, I will finish and answer any questions that I can. Yes, Alex.
Have you looked at the structure of your catalyst prepared by this carbonate route and compared second, third, first generation and your best competitors?
Yes, we have. We have.
And what have you learned?
I've learned. I don't know what I've learned.
What do you see?
I can't go into that, but it's very. There's some interesting things that we're seeing that I don't understand, and I wish I could talk to you about it because I'm sure you'd have some ideas that I am really quite baffled about. But what we think is happening is we think that this preparation gives us some degree of migration, allows us to get improved alloying, and we get that improved alloying between the palladium and the gold. But again, there's certain things that it's one of those things we were talking about, Frank. The more you know, the more you don't understand. And so I think that's the answer I can give you right now.
Steve, I was curious, if I understood the chart right, as you scaled it up, the selectivity got better,
Right.
and so on. Were you working with the vendor and changing the preparations, or was it just luck that it got better? I'm curious to know why it got better as you went to larger scale.
I believe it's to do to
I'd like to know how to do that.
Yeah, to improve mixing. We work with 100 to 300 grams, and we're working with a little dish, and we're trying to put a liquid into a solid, fill the pores, and get homogeneous mixing. And then once we put it into a furnace, you want to get uniform heating, so that every sample seems the same environment. We have a very difficult time doing that in the small scale. In the large scale, it actually turns out to be much easier. So I believe it's the mixing effect.
Why not even go to the bigger batch?
That's a good
You
question.
think you're optimized there?
No, probably not, but I think it's logistics. It's logistics.
Further questions?
Oh,
So, the vendor can make a better catalyst because you got better mixing dynamics and you come up with a different way of precipitating. I think I heard you say, and I just wanted to confirm this, you think maybe one of the reasons for the enhanced performance is that the metal distribution is different than what the original catalyst was? I'm not too familiar. Is it a uniform distribution or a shell distribution?
for us, it's a uniform distribution.
Is it?
And no, I don't believe the distribution is any different. I believe the alloy, the interaction of the palladium and the gold are different. But no, the distribution, as far as we can tell, it's fairly uniform.
Further questions? I'll ask another
Yes.
one.
Maybe this one you can answer. Is it known from the literature whether CO2 will make polycarbonates of metals like gold or palladium? In other words, from your cartoon, it's very appealing, but is there